Thank you very much. So, well, I'd like to start by thanking the organizers for having me here. Of course, it's a great honor to be invited to talk at IGST, and it's also a pleasure to be back in this wonderful city. So today I'd like to talk about some work in progress with Thiago Fleury in Brazil, Erkan Kalous, my student from Paris, and Didier Nasserman, about behavior of correlation function in planar n equals to 4 superior mills using our favorite method, which are hexagons. So we'll say a few words about hexagons, but very quickly. And hopefully trying to say something about some general properties they may have at finite coupling in some kinematics. Okay, so I try to put all of this in order. But I'd like to start with some disclaimers. So this is really a work in progress that we started not so long ago. So it does look a little bit like that at the moment. So if you don't know this painting, this is House of Parliament. I guess if you don't know this painting, you don't know this is House of Parliament, probably, although it's a famous painting. And well, this is where we stand at the moment, so don't be too tough on us if it is not super sharp. I believe that with more time and more integrability, we'll be able to say something clearer and hopefully find some beautiful Gothic architecture behind this painting. Okay, so here I start with a few slides of motivations. So the overarching goal, of course, is to try to understand this proposal by some people in the room, including Shota, Komatsu, Thiago, many others, for studying correlation function of single trace operators in the large n limit of n equals to 4 superior mills. So I say large n because I will be talking about planar limit mainly, but there is also, as you probably know, a very nice story about 1/n correction. So it's really a technique, a tool that builds on the string theory intuition that we can think of large n diagrams as being organized into topologies at large n. And the technique is very powerful in the sense that it is very flexible and allows us to essentially cover a lot of things. Whether we can compute concretely is still a very open problem, and this is essentially what we are trying to understand here in some situation. And the basic idea, so it's called hexagonalization. It means essentially putting a hexagon together. And the idea is pretty simple. It is based, again, in the strict large n limit when we consider only the spheres. It's based on the idea that planar spheres is a bit redundant, I guess, anyway. The spheres, which are punctured by a single trace operator, can be triangulated using hexagons. So here is a cartoon, the simplest example of hexagonalization that we may have for a 4-point function. So each operator here, single trace, is represented by a spin chain state, or a string state, if you want, 1, 2, 3, 4, which has, well, again, the usual single trace operator, half BPS operator made out of product of complex scalar fields. And so they contract with each other, like with contractions. There can be many other stuff on top of it, like gluons. But the idea is that essentially what we will get is a triangulation of the object. So here we get a triangulation with 4 triangles, 3 in the front, 1 in the back. And because each operator has this thickness, intrinsic spin chain thickness, there is actually a piece of the apex here of the tip of the triangle, which is replaced by some new segment, and that gives us what we call a hexagon. Okay? But so the hexagon has 3 sides that live in space-time. This is a triangle, space-time-wise. It also has 3 corners which live in a different space. Put together, it's an hexagon, but graphically, it's more like a triangle if you want to reduce the puncture to what they should be, which is just a point. So why do we like this picture? Because, well, first of all, we feel like it has something non-perturbative in it, like it should be applicable to any type of, the sum of any Feynman diagrams in this theory in the planar limit. And besides, thanks to integrability, these 25 years of integrability, 25 or 20? 20 years of integrability, 23 maybe, I forgot, has allowed us to develop powerful techniques, including this hexagon construction. And so we believe we know these hexagon form factors at exactly as function of the tough coupling. Okay, so these building blocks, these patches here that we want to put together, we think we know them at any value of this tough coupling constant. The problem we are facing now, it's not really a conceptual problem, but it's a real technical problem, is to actually glue these things together. Because the rule for gluing entails inserting a complete basis of state here along these edges, which we call mirror cut of the triangulation. And there are many states we should sum over. These mirror magnons can propagate from one triangle to another or from one hexagon to another. We should sum over them. And although there is some beauty attached to it, like some supersymmetry that is left and so on, turns out to be extremely difficult to perform these sums in practice. Okay. So what we need are techniques to figure out what we should do, also maybe some roadmap for where to look at simplification and how they could come about. So one first simplification that have been noticed already a few years ago is that we can somehow make our life simpler if we consider large charge correlators, or if you prefer discorrelators instead of the full clustering correlation function. So the idea is to just look at one part of the diagram that I was writing before, so just say the front or the back. Imagine we can, for somehow, by tuning the charge of the operator, engineer a configuration that is such that we get a lot of stuff here on the boundary, which make it impossible for the magnons to propagate from the inside here to the outside, and so isolate some piece of worldsheet of a form of a polygon that we can study more quietly using hexagons. Okay? So by doing so, we are killing some cycles. Cycles are bad in practice. I mean, they're often source of complications. It's not necessarily true for the hexagonalization for protected operators, but yet it is definitely a complication in the sense that we get more hexagons to put together. So no cycles here in my talk, just some hexagons that we put together, or if you prefer triangles, such as to form some big polygons. Not necessarily super big, but let's say bigger than the starting point. And this also, if we succeed to understand maybe the structure, this may be also building blocks for correlation function of short operators, assuming we can then start adding stuff on the boundary, put things together. It may also be part of something that some of you might like, which is correlation function, on a defect, like a Wilson line. So for that, you will have to put actual dynamical boundaries here, like the Wilson line, that will interact with the inside. And so that will change a bit the physics of the problem, but this is still part of this calculation is relevant for that defect correlator. Another reason to like this object is due to a proposal by Frank and Simon, which is that there is some evidence, I would say important evidence, that this object can also be interpreted as scattering amplitudes. So scattering amplitude in some sort of dual space, and for a theory that will live on some Coulomb branch. I will not enter into the details, but this is something that we should keep in mind, and Frank and Simon are providing evidence for that there should be some connection between this object and scattering amplitudes. Which connection precisely? Well, that's something maybe we should work out and make more precise. And again, this is a toy model for exploring this resummation because there are much fewer obstacles, I would say, or channels. Okay, so here's a prototype. So we heard a little bit about it already in the previous talk. The prototype of this object is a large charge limit of the 4-point function. So this is this limit where the 4-point function factorized into 2 octagon, which was introduced by Frank and further studied by a lot of people. And what is extremely nice about it is that it can be computed exactly. So everything I told you about this summation of states, mirror states here, end up essentially reconstructing a freedom determinant of a Basso kernel, precisely the type of determinant we heard about in the talk by Basso. So this is very encouraging, you would say. This is showing that there is a lot more to say about this hexagon approach. There could even be something that does not care anymore about hexagons, that builds essentially on some functional property of this determinant. So let's be optimistic that such a thing may be found in the future. But at the moment, I would say that it's extremely hard. There is a gap, a serious gap, between this computation for the octagon and the computation for the higher polygons. Okay, so it's extremely difficult to generalize this analysis to higher polygons, even the simplest ones that will be a 5-point function. Okay. I should say that there are nonetheless some very important results that have been obtained over the years, and which indicate that there are things that want to be found there. It's not just hopeless, of course, but there is still a gap in practice. So in order to learn a bit more about what type of difficulty we have here, we may try to look for more exact results. Some of these results, that exist when we go to a particular kinematics. So instead of trying to do generic kinematics, which may be too ambitious as a starting point, we may try to find some corner of the kinematic space where things want to simplify and perhaps tell us something about the resummation technique we should find. And here again, there is some indication we can get from the octagon and from the paper by Frank, which is about this null square limit, where the two cross ratios of the 4-point function are going to 0 simultaneously. So this is a limit, again, where the polygon literally becomes a null square. Okay. And Frank observed through many loops, and later on, people here proved it, that the log of the correlation function is quadratic in the logs of these small cross ratios. And is entirely controlled by a single coefficient of the coupling, which is this octagon anomalous dimension. On top of that, this octagon anomalous dimension is a very, very gentle object, I would say, since it admits an extremely closed expression, which is given here. Okay. So this is evidence that some nice thing may happen, and also even some bonus, I would say. But of course, it's still the octagon, and you may think that, okay, you say that it is extremely simple, that it's not a good example, I would say, for the rest. But yet here there is something that is also resonating with some behavior that was observed in the context of scattering amplitudes, which are not known to be especially simple in this theory, although they are subject to important simplification. Which indicate that we may believe or may expect that this type of behavior will generalize to higher point functions. And here, this is what I would like to explain in this talk, which is discuss this generalization by also mentioning the links with what we called in our previous paper with Lance, Andy, and Yorgos, origin limits of scattering amplitude, which is a generalization of these light-like limits, if you want. Okay, so some particular corner of the kinematic space where we should expect and we should be able to prove that correlation functions simplify and take a very pleasant form. Okay. So here's a rough plan. I try to follow it. So I will start with some kinematics. Then I will explain what we've been able to do. So this is just about trying to classify a little bit, what type of limit are we talking about? How many are there? Just get some rough idea of what they could be and how to describe them. And then there will be some hardcore integrability, which I will try to keep as light as possible, mainly because we don't have so much result yet. And of course, conjectures, which are free and always great to make. And also some other conjectures. Okay, so what type of origins are we talking about here? So what type of limit? So here it's important to say from the very beginning that I'm going to stick to a particular subkinematics, which is a 2D kinematic. So for 4-point, it's not really a restriction. We can always put 4-point in a plane. For higher point function, it is a huge simplification, especially at the level of the hexagon construction. And we are going to make this assumption here, by keeping in mind that there may be an even bigger world outside there waiting to be explored. And in 2D, we have a lot of techniques for describing the geometry. Here I'm reviewing some basic facts that should resonate. So in particular, since we are in the plane, we can go, to spinor variables. Or if you want to point on CP1, the projective plane, and describe this way the left and right moving coordinate of our vertices. So we have vertices in the plane. They have ZZ bar coordinate, if you want, or XX bar coordinate. And we can describe them in terms of spinors, modulo some projection symmetry that allows us to fix the North Pole, essentially. Equivalently, we may package all of these guys, the left or equivalently the right part, inside some 2×n matrix, which is just some Grassmannian. Again, modulo this torus action that is just this projective redundancy, which here I use, for instance, to fix every top here to 1, except this one, which you should think as a point at infinity. So this is a point at the origin of the plane, if you want. This is a point at infinity. This is just 1. And these are the other points, which I'm putting a bit randomly. So we get 2 copies of these spinors. And we need both of them to reconstruct the actual distances in the problem. So the actual distances are the product of these angle brackets, 2 types of angle brackets that we get by just doing spinor contractions here. Okay. So I should say, the conformal group here is acting just as SL2 times SL2 on this object. So this is the great thing about these variables, which is that we can just linearize the action of the conformal group on them. So beside this, natural embedding or representation, there is also another important thing that comes with our triangulations, with our hexagonalization, which again start off with a triangulation, which is that each triangulation comes with a natural set of cluster coordinates, which serve precisely to, they just serve to parameterize the geometry up to conformal redundancy. And in this construction, each coordinate is associated with a cut or chord in the triangulation and is given by a very local rule. So you just look at which chord you are talking about, and then you construct the cross ratio, using the other element of the triangulation that's around it. Okay, so here, for instance, the variable ZAB, the cluster coordinate associated to A and B here, this chord, is just given by this product times this one divided by this one and that one. This is just this cross ratio here, if you have never seen it before. So actually, these are natural coordinates in the hexagonalization. This is what determines the weight of the mirror magnon. So when we use hexagonalization, for every cut, as I say, we have a sum of our mirror magnons, and each one of these mirror magnons is weighted by something which is related to this Z. Okay, so when we change the geometry, we change the way we weight these magnons, and there are especially some limit when Z is small, for instance, where the weight is very negligible, so we control very well the sum of all the magnons. There could be other regime, like when Z is large, where we need to resum or do something to understand what is happening. Okay. This is something that we may want to do in some situation is a mutation. So this is a transformation that exchanges essentially Z small to Z large. And it maps cluster coordinate of one triangulation to cluster coordinate of another triangulation associated with a flip. So this is a basic example where you introduce a coordinate for this set of chord here. You do a flip, which is just a change of triangulation, and you get new set of coordinates, which are related by some algebraic relation. Oh my God, 10? Okay, so this is all very basic, you agree? So this is the exchange graph of the cluster algebra. We get some A1, here we get some A2, which is a pentagon. And what is important is that we can think naturally of the kinematical space as something that will fill the inside of this picture. So in particular, here this mutation will be like at the boundary of the picture, and the physics inside will be called the positive region. So a cluster origin is something that we can identify with a point at this boundary. So, and this is at the boundary that we expect singularities to develop typically. Inside, everything should be smooth. So there is another way of thinking about this point at the boundary, which is quite nice and which is based on this binary geometry. So in this case, we should define some cross ratios by using a cross ratio which are associated with chord, again, by using this formula. So in this case, we take point at the boundary of the polygon, and we construct this particular quantity. Doing so, we get too many cross ratios. It's overcomplete. And we find some elegant constraints on them, which relate the cross ratio of the segment ij and the product of all the cross ratio of the segment or chord that intersect ij. Okay. So why is this relation very important? It's important because if we now go to the boundary by sending a u to 0, we find that all the other u which are incompatible or crossing that chord are going to 1. Okay? So in particular, vertices on the boundary will correspond to the choice of a binary sequence in which n-3 cross ratio vanish, so they go to 0, and all the other ones are going to 1. So as I say, we get left and right geometry to take into account. The physical cross ratio are the product of the two. So in practice, if we want to maximize the number of cross ratios that are going to 0, which is something that we want to do as a simplification to begin with, we should choose for the left and right geometry two triangulations which have no chord in common. Okay? So this is what I will call an origin here. So here's an example, for instance, where I have like a chord 1,3 and a chord 2,4 here. So they clearly cross. So they will maximize the number of u going to 0, and indeed we get 2u going to 0 here. For the 5-point function, I can make this choice for the left part and the right part. And what I will find is that I will find that 4 cross ratio are going to 0 and 1 is going to 1. There is always one line here, which is not, for instance, 3, 5, which is neither a chord here nor a chord there, and which has to go to 1. Okay. So at higher point, we usually get more possibilities because we can choose these two triangulation in many different ways. That gives rise to a lot of interesting behaviors that of origins, of candidate origins, that we may want to study. Here I'm only giving 2 as an example, but there is in principle more that needs to be classified. So what do we want to do next? So we have these origins, and we want to explore how the correlation function behave in these limits. This is something that proves to be very difficult. If we have a big polygon with many origins, we need to explore them all. All of them will correspond to various behavior in terms of the z coordinate, which I introduced at the beginning for a given triangulation. So in general, it's hard to do, but at one loop, there is a nice formula that was worked out, and which allows us to essentially express any computation in terms of block Wigners. And there we can just take our origins, plug the behavior in terms of the z, so we have to scale the z in some limit, in some way to get to the point we're interested in. And then check that this is actually becoming quadratic in logarithms, as we will expect from the generalization of what was observed for the octagon. So there is more we can do in principle. So here I will go a bit fast because I'm already late. So we can use the hexagons at higher loop to try to do some computations. This is a tough computation, but we can develop some techniques, some trick, and verify in particular this result of rank and so on, that the 4-point function is controlled essentially by 2 coefficients, simple function of the coupling. And then we, oops, okay. Anyway, forgot it. Okay, so this is showing that what we expect is, of course, there for 4-point functions. That was our inspiration. Then we can go to 5-point function and start observing what happens. So we can do this, try these techniques of simplifying the sum over the mirror magnons in the limit we're interested in, see what comes out. Of course, this is in practice relatively difficult. But again, this is something we can do up to a certain number of loops just by turning the crank and sweating a little bit. And so far what we observe is that indeed the result wants to exponentiate, and the exponent is quadratic in the logarithms. So we pick an origin. This is defining a certain limit. And then when we analyze what happened in this limit, we indeed find that the result exponentiates and that the exponent is quadratic. And the structure is, again, very similar to the origin in scattering amplitudes. And so we may expect to be able also to accommodate it under the umbrella of some big conjecture. So what is this conjecture? So this is where we started to speculate a lot. But of course, after speculating, we'll have to do calculation. So here I'll be fast because it takes a while to understand this formula. But what it expresses essentially is how to construct a quadratic ansatz for this log of the amplitude in any origin limit in terms of two building blocks. One is this tilted cusp, anomalous dimension, that was introduced in the previous slides, and which was also appearing somewhere here for some specific values. And the other one is what we call the string integrand. This is something that we can construct in principle from some sort of string theory description as strong coupling, which is based on the TBA. What? There is an entire slide here. Okay. That's anyway, let's keep going. There is a string integrand, which is based on some potential minimal surface description that we are still looking for. We don't know how to characterize it for a string theorist, like tell what he should be computing, he or she should be computing to get the result. But we can use integrability to cook up the answer. Okay? And from there, we can read off this important information about the string integrand, which we can put under this integral transform together with this tilted cusp anomalous dimension, which was synthesized here to this formula. And get the answer. Okay, so I told you that this will be a bit impressionistic. Yeah, so there's some hole in the description. Anyway, the end result is this. Okay, log of the object is a sum over some alphas. Which alphas? Well, you need the TBA description to figure out. Some polynomials, no coupling here, just string theory prediction, and this generalization of the BES cusp. This tilted BS cusp anomalous dimension. Again, everything in principle is predicted. I just clearly don't have time to predict it now. But here is, for instance, what we got at 5 points. So we get this funny alpha, pi over 12, 5 pi over 12. Who can guess this? But magically, and also some polynomials, this is just to show that there is a bit of calculation behind that. And this is actually matching through 3 loops. The data that we had, and we are now pushing it to higher loops to make sure that everything is safe. Okay. So anyway, there is more to say, obviously, but it's time to conclude. So the planar disk is an interesting area, I would say, for studying resummation techniques at the level of the hexagons construction through this origin limit. So there are some important simplifications here that I've mentioned, which make it easier compared to the problem we had for scattering amplitude. One of them is that we have a simpler cluster algebra. We have these U coordinates, which are extremely nice to label the point at the boundary by some binary sequence. Everything is very transparent, and again, easier to depict and think about. And so the next step is to study how the correlation function behave in this limit, and in particular in all these origins. So for what we can say, what we are seeing is consistent with scattering amplitude behavior. We do get this nice exponentiation and quadratic in log behavior. And it is also consistent with an all-order formula. What we don't have yet is a complete dictionary and a lot of evidence, I would say proof maybe, that this is correct. So because as you go to generic n, you get plenty of origins. You need to put them in correspondence with some TBA, some saddle point of the TBA equation, and show that this is going to reproduce the actual result. So this is where we need to do some more, I would say, realistic job, which is to try to prove. I don't know how much we can prove here, but we can certainly test many things and possibly also bootstrap some part by some consistency condition. There are, again, some other limits which are worth considering, which are not exactly origins, but which are closely related to them, which are this null or light-like limit, and some relation to pentagon OPE, but that I will leave for another talk, I guess. Thank you very much.
Okay, we have time for some questions. Well, since you felt rushed, you have 5 minutes. Would you like to talk about something in a little more detail?
I'm not so sure. That's weird, actually. No, I don't really. Well, no, I think it's good like that.
Okay, Carlos.
So when you do the amplitudes in the origin limit and you see this many gamma alphas appearing, and when you see here like a large charge, do you see the same times of gamma alpha? Do you see different times of gamma alpha? For example, 6 points?
Yeah, so the gamma depend on the saddle point. In fact, this is really the string theory saddle point that determines which alpha will show up on, which alpha will turn on and which one will not. And the TB equations are different between the two problems, so they are going to predict different behavior. What I can say is that this gamma oct appears quite often, but not always, not all the time. And also at higher n, it often appears with many other alphas, not just gamma oct. So this is somehow related to what is written here, which is that the problem is not just controlled by gamma oct. Naively, there was this idea, okay, maybe you replace gamma cos by gamma oct, and you understand the general structure of these limits for this new kind of amplitude-like object that we have here. But the structure is less universal, is more complicated. It involves many of these gamma alphas. And again, the alphas depend on the limit and the number of points and so on. And why is it so? I don't know. I don't have a general understanding. At the very best, we have this conjecture. If correct, it's predicting the result. But now, someone has to analyze it.
Okay, so if there's no more questions, let's thank Benjamin.